Hey, welcome back everybody. In this lesson, we're going to work with identity and inverse matrices. We'll see what both identity and inverse matrices are, and we'll see how to find inverse matrices if we start with a matrix that has an inverse. Inverse matrices have a lot of interesting applications both in algebra and some simple encryption, and we'll see that in following lessons. But for now, let's get started. Okay, so our lesson today is going to focus only on square matrices. Everything that we're going to talk about only applies to matrices that have the same number of rows as columns. And so if you have a square matrix with ones on the main diagonal, like right here, then if you've got zeros everywhere else, then we call that an identity matrix. So I've shown four identity matrices here. Each size square only has one identity matrix. So right here, I subscript 2, that is the identity matrix for a 2 by 2 square matrix. I sub 3, there's the identity matrix for a 3 by 3 sized matrix. There's I4, and even if your matrix is only 1 by 1 square, then it still has an identity, and it's right here. So you can see that the pattern for all of these is exactly the same. Now, the identity matrix plays an important role in matrix arithmetic because they have a really unique property. In fact, they're the only matrix with this property. Let's see what that is by doing some multiplication here. So let's start with this 3 by 3 identity matrix times another 3 by 3 square matrix. Remember from our work in our previous lesson, if we want to multiply two matrices, is we give the size of each matrix, these two middle numbers have to be the same, and that is certainly the case. So a 3 by 3 times a 3 by 3, that multiplication can be performed, and our result will be a 3 by 3 matrix. So a quick refresher on how that multiplication will work out. You might want to rewatch the previous lesson if you don't remember how to do matrix multiplication, but I'm going to take the top row of our left matrix and find the dot product with the left column of the right matrix. And so I'm going to take 1 times 4, 0 times 3, and 0 times 7, and that gives me a top left entry of 4. To find the top middle entry in my product matrix, I'm going to take the top row and the dot product with the middle column. And so I'll have 1 times 2, 0 times 5, and 0 times 9 gives us a value of 2. The top right entry will be top row times right column. 1 times 6, that's 6, plus 0 times 8 plus 0 times 0, that's 6 plus 0 plus 0, that's 6. What about row 2? Now I'm going to take the middle row of the left matrix and find the dot product with the left column of the right matrix. And so that's going to be 0 times 4, which is 0, 1 times 3, which is 3, and 0 times 7, which is 0. That's going to leave me with a 3. Middle row, dot product with center column. 0 times 2 is 0. 1 times 5 is 5. 0 times 9 is 0. So that's a 5. And at this point, I'll bet you can see what is happening with our identity matrix. Middle row, right column, find the dot product. 0 times 6 is 0, 1 times 8 is 8, and 0 times 0 is 0. Bottom left entry, bottom row, left column, dot product. 0 times 4, 0 times 3, 1 times 7. Bottom row, middle column. 0 times 2, 0 times 5, and 1 times 9 is 9. 0 times 6, 0 times 8, and 1 times 0, that turns out to be 0. And there it is. There's our product matrix. Notice anything? Well, sure enough, our product matrix is exactly the same as the matrix we multiplied our identity by. Let's see if that's also true by our 2 by 2 example. Now, notice that I put the matrix that I was multiplying the identity by on the right. I put the identity on the left. Does it matter? Let's switch the order for a 2 by 2 example and see how that works out. So for our second example, we're taking a 2 by 2 matrix times the 2 by 2 identity. We know that these two middle numbers have to be the same, and of course they are, and that tells us that our product matrix will be a 2 by 2 matrix. And so here we go. Again, we're going to take dot products. To find the top left entry, we'll take top row and the dot product with the left column. That's going to be 5 times 1 plus 2 times 0. That's a 5. top right entry is top row dot product with the right column. That's 5 times 0, which is 0, plus 2 times 1. Bottom left entry, 4 times 1, which is 4, plus 8 times 0. And sure enough, bottom right entry will be 4 times 0 plus 8 times 1 is 8. And so here again, the product matrix turns out to be the same as the matrix we started with. So the identity matrix really acts like the number 1 does for real number multiplication. Anytime you take 1 times a real number, you get the very same number. 1 times 4.75 is 4.75. We call the number 1 the identity for the real numbers. It is the number that when multiplied leaves you with your original number. And that's why we call a matrix like this one the identity matrix. When you multiply it by a matrix, you'll end up with the original matrix. And so for our last example, 4 by 4 identity times a 4 by 4 matrix, we really don't need to do the whole argument. We know that these two can be multiplied and that we'll end up with a 4 by 4 product. Now, if we start that multiplication, as always, we're going to take top row by the left column. That'll be the dot product. 1 times 0, which is 0. 0 times 7, 0 times 1, and 0 times 2, those are all 0. And we really don't need to go through this whole argument, right? We could do these 16 dot products, but we just showed that the identity matrix times another square matrix of the same size will leave that matrix unchanged. So we can just say, because we know that these entries will be the same, or these elements, that we're going to have the very same matrix as our product. And we're done. Not because we did all the multiplication, but because we know how the identity matrix works. Okay, so now that you know what an identity matrix is, we can look at a little bit deeper property of matrices. Let's take a look at inverses. Think about what you already know. Every real number, except 0 of course, has an inverse, which we call the reciprocal. And you know that when you multiply a number by its reciprocal or by its inverse, you get a result of 1. So for example, what is the reciprocal of 2/5? Well, if we take 2/5 and its reciprocal, that would be 5/2. And if we multiply 2/5 by 5/2, we get 10/10. In other words, we get 1, right? And that is the identity for real number multiplication. What's the reciprocal of 9? Well, the reciprocal of 9 is 1/9. And 9 times 1/9, of course, that is equal to 1. So again, we get the identity. But notice that there is nothing we can multiply 0 by. 0 has no reciprocal that I can multiply to get the identity, because 0 times anything will be 0 and it'll never be 1. So not all numbers have reciprocals, but most do. The same thing is true for matrices. Most square matrices have inverses. And it's worth noting that if our matrix isn't square, then it's impossible for it to have an inverse. But those that are square will often have inverses. We have a name for that. If we call our square matrix M, then the inverse matrix we call M inverse. And that, by the way, is the same notation we use in algebra. If we have a number x, then the reciprocal of x is called 1 over x, but we also sometimes call that x to the -1 to show that it's the multiplicative inverse. So that exponent -1 notation is kind of familiar. It's the mathematical way of expressing an inverse. Now, when we talk about real numbers and we want to know its inverse, it's easy. We just flip it over to get the reciprocal. You know how to find the multiplicative inverse for a real number if it exists. But how do we find the inverse of a square matrix? Now, that's a little bit more work, and that's what we're going to spend the rest of this lesson on. It's time for you to become familiar with what are called the 3 elementary row operations, or 3 row operations, which we can use to transform the way a matrix looks. First of all, we can change the position of any 2 rows. We can just swap rows, and that's no problem. Any row can be multiplied by a non-zero constant, and we can add a multiple of one row to another. Now, these kind of seem like arbitrary things to do, but these are 3 powerful tools for manipulating matrices. We're going to use these in the next few lessons. So let's find the inverse of the matrix 2, 4, 1, 3, a little 2 by 2 square matrix. The first thing we'll do is we're going to rewrite this matrix immediately before the identity matrix of the same size, like this. So I'm really forming a 2-row, 4-column matrix here with the original matrix on the left and the identity matrix for a 2x2 on the right. Now I can use those 3-row operations to change this left matrix into the identity matrix. And that's going to mess up the right side, but that's okay. So here we go. Here's our 3-row operations that were allowed. Now remember, I want this identity matrix to end up on the left, and I can only do that by using these 3-row operations. It kind of feels like a little bit of a game, so here we go. In general, it's best to work from left to right, starting with your 1 and then following by the zeros. And so let's do that here. Do you see a way that we can get a 1 in the top left using these 3-row operations? Well, hopefully so. We can switch row 1 and row 2. That's our first allowed operation here. I'm going to use the notation R1 and R2 with a little double arrow, and that's the notation to show I'm switching row 1 and row 2. It's a way of keeping track of what I've done. So that means 1, 3, and this stuff on the right, 0, 1, moves to the top, while 2, 4, 1, 0 drops to the bottom. Okay, I have the 1 in the top left. That's what we want. Now, how can I get a 0 below this? Well, switching rows won't do any good. That will just put us back where we started. Option 2, multiply any row by a non-zero constant. There's nothing I can multiply this row by that will make that a 0 except 0, but that's not allowed. So I have to rely on my third operation here. I can multiply a multiple of one row by another. So I can add -2 times row 1 to row 2. -2 times 1 is -2. That'll put a 0 in the bottom left. And so my notation there is going to be -2 times row 1, and I'm going to add that to the numbers in row 2. Here we go. We're going to do this mentally. So -2 times 1 is -2, plus 2 is 0. -2 times 3 is -6, plus 4 is -2. -2 times 0 is 0, plus 1 is 1. And -2 times 1 is -2, plus 0, that's -2. So I've changed this bottom row. The top row did not change. 1, 3, 0, 1 is still in place. Now you'll notice our left column is done. We have a 1 and a 0 there. Now I'll continue my process up here. So now we want to find a way to move on to the next column. We need a 1 in this bottom right spot. We move from left to right, always getting the 1 and then the zeros. So how can we change this into a 1? Well, let's make use of our second row operation. We can multiply any row by a non-zero constant, and that's allowed. So multiplying this by half would make it a -1, but multiplying it by -1/2 will make this a +1. So 0 times -1/2 is 0. -2 times -1/2, that's a 1. That's the one we want. 1 times -1/2 is -1/2. And -2 times -1/2 is a 1. Now I didn't tamper with the top row at all, so that's 1, 3, 0, 1. And we're almost there. We've got 1s on the main diagonal and a 0 down here. We just need to get a 0 in that position where the 3 is, and we'll be done. So how can we do that? Switching rows isn't going to do us any good. We can't multiply this by anything that would give it a 0 because that would mess up our 1, and we can't multiply by 0. So we're going to rely on our third option here. A multiple of one row can be added to another. So let's take -3 times row 2 and add it to row 1. That'll put a 0 in this spot without changing our leading 1. So -3 times the value in row 2 times the value in row 1. -3 times 0 plus 1 is 1. -3 times 1 is -3, plus 3 is 0. Negative 3 times negative 1/2, that's positive 3/2 plus 0. And negative 3 times 1 is negative 3, plus 1 is negative 2. And we didn't change row 2 at all, so we have 0, 1, negative 1/2, and 1. Okay, we did it. Now we have the identity matrix on the left side instead of the right side. And surprisingly enough, what we have left on the right side, that is our inverse matrix. So our original matrix M was 2, 4, 1, 3. We can conclude that the inverse matrix, M inverse, is 3/2, negative 2, negative 1/2, and 1. Now, you should be asking yourself why that matters at all. Well, inverse matrices can be used for a few things, which I'm going to show you in the next few lessons, but here's one property. Since the inverse of a matrix kind of acts like the reciprocal does for whole numbers, it's always true that if we multiply a matrix by its inverse, we'll get the identity matrix. Let's see if that's true. Okay, let's take our original matrix M times the inverse that we just found and see what we get. Now I'm going to show all of our dot products here because there's a lot of arithmetic in this and I want to make sure that you follow the fraction work that we're going to do here. So if we find the dot product of the top row and the left column, we have 2 times 3/2 plus 4 times negative 1/2. And if you do that, you'll get 3 minus 2, the top left entry is in fact a 1. What about the top right? Top row dot product with the right column, that's going to be 2 times negative 2 plus 4 times 1. That's negative 4 plus 4. That is a 0, exactly what we'd hope for in the top right. The bottom left, let's take the dot product of the bottom row and the left column. That's 1 times 3/2 plus 3 times negative 1/2. That's 3/2 minus 3/2. The bottom left turns out to be 0. And the bottom right, that's 1, 3, dot product with negative 2, 1. 1 times negative 2 plus 3 times 1. And sure enough, that's negative 2 plus 3. That gives us 1. And there it is. Look at that. We got the identity of a 2 by 2 matrix. And so it worked. A matrix times its inverse gave us the identity. Now I won't take the time to do this, but the order doesn't matter. If we were to switch these matrices and multiply them together, we'd still get the identity matrix. Okay, let's do the same process again, but this time let's work with a 3 by 3 matrix to start with. So here's our matrix: 0, 4, negative 2, 2, negative 6, 4, 0, 1, negative 1. Let's find the inverse matrix for this given matrix M. Again, we need to write our matrix immediately before the corresponding identity matrix. So this is going to be our matrix, and then we're going to augment it, it's called, when we just tack on another set of columns. And that'll be our identity matrix for a 3 by 3. And there it is, 1, 1, 1 with zeros everywhere else. Okay, here we go. Once again, we want to start moving the identity matrix to the left, but we have to use our 3 allowable row operations, and we always start by getting the left column straightened out, then the middle column, then the right, and we always get 1s, then zeros. So how can we get a 1 in the top left of our first column? Well, we've got a couple zeros to work with, so what we could do is we could multiply everything in row 2 by 1/2 to change that into a 1, and then we'll just swap it with row 1 and it will be right where we want it. So our notation there will be that we're taking 1/2 of row 2, and that'll give us half of 2 is 1, half of negative 6 is negative 3, half of 4 is 2. Now, those moves continue through the rest of that row. Half of 0 is 0, half of 1 is 1/2, and half of 0 is 0. So we modified row 2. We did nothing to row 1. That stays the same. And we did nothing to row 3, that stays the same. Now we have a 1, 0, and 0, but it's not in the right spot, so let's switch row 1 and row 2. So row 2 goes up to the top, row 1 drops down to the middle row, and row 3 doesn't move at all. Our notation there is that we took row 1 and we switched it, double arrow, with row 2. Okay, so our first column is ready to go. Let's move on to our second column. We want to get a 1 in this position and a 0 above and below it. So how can we get a 1 in this position? Well, we could multiply that by 1/4, which would get us a 1, but then we're going to have some more fractions, and we try to avoid those. There is a 1 right down here. Let's just switch row 2 and row 3 to get the 1 in this position instead of that position. Okay, there it is. We switched row 3 by moving it up 1, and row 2 dropped down 1. We swapped row 2 and row 3. Row 1 remained the same. Now, it probably goes without saying, but matrix operations are an exercise in attention to detail. Losing one sign or transposing two numbers really messes this up. So really double check your work as you go and make sure that you haven't made any mistakes. It can be very frustrating. All right, we got our 1 here in column 2. Now we need a 0 above and a 0 below. So we're going to leave the middle row just the way it is. And let's go ahead and change that top entry to a 0. The best way to do that, you'll maybe start noticing a pattern here. We're going to multiply row 2 by 3 and add it to row 1. 3 ones added to -3 will give us a 0. So we're going to take 3 row 2 and add it to row 1. So 3 times this row 2 entry is 0 plus 1. That doesn't mess up the 1 that we wanted. 3 times 1 plus -3 is 0. 3 times -1 is -3, plus 2 is -1. 3 times 0 plus 0 is 0. 3 times 0 plus 1/2 is 1/2. And 3 times 1 plus 0, that's 3. That looks good, and you can see we're starting to get our identity matrix over here. Now, let's continue on. Let's do the same basic idea to get a 0 down below. Let's take -4 times row 2 and add it to row 3. So -4 times row 2 plus row 3 will set us up here. So -4 times 0 plus 0 is 0. -4 times 1 is -4, plus 4 is 0. -4 times -1 is 4, minus 2 is 2. -4 times 0 is 0, plus 1 is 1. -4 times 0 plus 0 is 0. -4 times 1 is -4, plus 0 is -4. Okay, so we're almost there. We've got 2 of our 3 columns all taken care of. Okay, now let's move on to our last column. We need a 1 here, a 0 here, and a 0 here. It might be tempting to say that we could multiply one of these negative ones by -1 and then switch it. The problem is that that would put something other than a 0 in these first 2 spots. So we're really limited to just changing this row. How can we change that 2 into a 1? Well, let's multiply row 3 by 1/2. So let's take 1/2 of row 3, and we won't change anything else. Half of row 3, half of 0 is 0, half of 0 is 0, half of 2 is 1, that's the one we want. Half of 1 is 1/2. Half of 0 is 0, and half of -4, that is -2. Okay, we didn't tamper with row 1 or row 2. And all we need now are zeros in these last 2 spots. So we definitely don't want to mess with row 3. That's exactly where we want it. So we'll leave row 3 just as it is. Now, how can we change this into a 0? Well, we have a 1 right below it. How if we just add row 3 to row 2? If we add 1 to -1, that'll give us a 0, and it won't mess up any of our previous work. So let's take row 3 and add that to row 2. 0 plus 0, 0. 0 plus 1 is 1. 1 plus -1, that's 0. 1 half plus 0 is 1 half. 0 plus 0, negative 2 plus 1 is negative 1. Okay, and row 1, well, let's do the same idea. Let's take that 1 and add it on to row 1, and that'll make that a 0 without messing up our previous work. So let's do that again, but this time let's take row 3 plus row 1. 0 plus 1 is 1. 0 plus 0 is 0. 1 plus negative 1 is 0. Look at that. We've almost got it. 1 half plus 0 is 1 half. 0 plus 1 half is 1 half. And negative 2 plus 3 is 1. So we've done it. We got our identity matrix moved to the left side, and that means that the inverse matrix of the one we started with is waiting for us right here. We can conclude then that our inverse matrix, M inverse, is 1 half. 1 half, a lot of 1 halves in this matrix. 1 half, 1 half, 1. 1 half, 0, negative 1. 1 half, 0, negative 2. And we found our inverse matrix. We did that by following those same 3 steps. We wrote our original matrix right before the identity. We used our row operations to convert that identity matrix to get it on the left side, and then our inverse matrix ended up on the right. Now again, our result should be able to be multiplied by our original matrix to get the identity, and so we know what our inverse is, we know what our original matrix was, we should be able to multiply those to get the identity matrix. But you already know how to do that, and I just want to make sure that you recognize that there are tons of websites and probably apps that can do this for you. So I like Symbolab. Let's go to Symbolab and check our results here. Okay, when you go to Symbolab, we can do matrix work by choosing matrices and vectors right here. And we're working with 3 by 3 matrices, so I'm going to choose the 3 by 3 option. And I'm going to enter our original matrix, which was 0, 4, negative 2, 2, negative 6, 4, and 0, 1, negative 1. Okay, there was our original matrix. And now I'm going to multiply that by another 3 by 3 matrix that was our inverse, which we found, and that is 1 half, 1 half, 1. There's our inverse matrix, and let's multiply those two. If we multiply them together, Symbolab shows us the result. And in fact, if you scroll down, it shows you all the dot products as well, which is kind of nice. So if we multiply these two matrices together, you can see that our resultant matrix, or our product matrix, is the identity. And so we got it. It worked out just fine. So you could check those by hand, but use Symbolab. It's also worth noting that you can use Symbolab to find inverses. If we just choose the inverse function, we'll get our full pad here so that we can type in a 3 by 3 matrix. We'll go and enter the original matrix. There it is, and go. All right, Symbolab says that this is our inverse matrix, and that of course matches exactly what we got. So don't lean in that too much. As it turns out, these row operations, which are tricky, have other applications that we're going to use in the next few lessons. So don't skip this process, but by all means use resources to double check your work rather than doing all that by hand. Okay, let's wrap this up. I'd like you to do one for practice. I'm giving you a matrix C here, negative 4, 0, 1, 2, just a little 2 by 2. That's all I'll ask you to do in the homework. I would like you to find the inverse matrix for this little 2 by 2 matrix. Pause the video, use your 3 row operations, do that and unpause to see the solution. Although you could check it yourself and know right away whether or not it works. Okay, here we go. There's our original matrix. We put that on the left. We put the corresponding identity on the right. Let's get to work. We want a 1 in the top left, so we can just switch row 1 and row 2. Let's do that. Okay, switching row 1 and 2 gets us the 1 in the top left. Now we need a 0 right below it. It's worth noting that you don't have to follow my exact steps. There's more than one sequence of row operations that do this, but just from experience, I'm usually showing the shortest way to do this. So we got our 1, let's get a 0 here. Let's take 4 times row 1 and add it to row 2. 4 times 1 is 4, plus negative 4 is 0. 4 times 2 is 8, plus 0 is 8. 4 times 0 is 0, plus 1 is 1. And 4 times 1 is 4, plus 0 is 4. And we're going to leave row 1 unchanged. So we've got our first column done. Let's move on to column 2. We want to get a 1 in this position, and so really the only way to do that is to multiply row 2 by 1/8. So 1/8 times 0 is 0. 1/8 times 8 is 1. 1/8 times 1 is 1/8. And 1/8 times 4 is 4/8, but that reduces to 1/2. We're not going to change row 1 at all. And so we're almost there. We just need that 0 in the top right spot. We're going to leave the bottom row just as it is. We don't want to mess with that. Let's take negative 2 times row 2 and add it to row 1. So negative 2 times row 2 plus row 1. Negative 2 times 0 plus 1 is 1. That didn't change, and that's good. Negative 2 times 1 is negative 2. Plus 2 is 0. There, that's what we want. Negative 2 times 1/8, that's negative 2/8, plus 0, negative 2/8, but that's the same as negative 1/4. And negative 2 times 1/2 is negative 1, plus 1 is 0. And so we got our identity on the left side. What ends up on the right is the inverse matrix. So the inverse matrix that you should have gotten is negative 1/4, 0, 1/8, 1/2. You could multiply that by the original to show you get the identity matrix, but we're done. We wrote our original matrix right before the identity. We used our row operations to move it, and our inverse matrix showed up on the right. Okay, well, that's definitely enough for this lesson, but just to summarize what we did here, you became familiar with the identity matrix. The identity matrix is that square matrix that acts with other square matrices just like the number 1 does with the real numbers. When we multiply a square matrix by the identity of the same size, we're left with the original matrix. And we saw that like the real numbers, most matrices have an inverse that we can multiply by to get back to the identity matrix of the correct size, and that is the inverse. And so we have a process for finding the inverse. We always write our original matrix right before the identity matrix of the same size. We use our 3 row operations, which are switching 2 rows, multiplying a row by a constant that's not 0, and adding a multiple of one row to another. Those 3 operations always allow us to get that identity moved from the right side to the left side. It allows us to do some other things too, as we're going to see in the next few lessons. And then after we've done that, then the inverse matrix reveals itself on the right side. All right, we practiced a few of those. It's time for you to practice a few more. A little bit of homework will be assigned. Make sure to let me know if you have questions. Tricky topic, but we're going to use these ideas in our next few lessons as well. So make sure to let me know if you have trouble. We'll see you in the next lesson.